All right, ladies and gentlemen, welcome back. So today we're going to pick up talking about action potentials, and this really is the nuts and bolts about how a neuron is able to send a signal. So when we look at action potentials, what does this really mean? Well, first off, it's the depolarization shift in the membrane's potential. What does that mean? Remember that the depolarization is going more towards that positive when we're looking at the differential in voltage on opposite sides of the cell membrane. So we're moving this direction as opposed to that hyperpolarization that would make it more negative. It also needs to be sufficiently depolarized enough. We have to get past that threshold point in order to actually substantially change the membrane's voltage. So here's the interesting thing about action potentials. First and foremost, they always have consistent magnitude. What does that mean? That means we're always hitting approximately this sort of level of depolarization once we've crossed over that threshold point. So it's an all or nothing event. Either I make it to that threshold, in which case I hit this depolarization and come back down, or if I never quite get to that threshold, then this action potential never gets sent. So long as I hit here, this happens. It doesn't matter what's coming in. I just need to make it past that threshold point. So it's all or nothing, and it's consistent every single time. The interesting thing about action potentials then is that these transmit signals over their long distances. So these are going to work across the axon itself. And this all happens by changing those ion channels. All right, so those ion channels are what we call voltage gated, meaning they open or close when that membrane potential changes to a certain level. In other words, we've hit that threshold. So let's talk about how this actually works step by step. So if I take a look at that graph and break it down into pieces and look at what's actually happening in the cell membrane itself, remember that everything starts at that resting potential. So what does that mean? That means that when I look at a resting neuron, a neuron that's not sending any sort of signal, the vast majority of those voltage gated sodium channels are closed. So they're not allowing sodium in and out. And most of the voltage gated potassium channels are also closed. So we're setting up this dynamic of overarchingly positive charge on the outside, overwhelming negative charge on the inside. And we're kind of just sitting there and resting as this goes. This is where I'm not sending any signal. As more signals come into that neuron, I may get to a point where I start to depolarize, meaning that some sort of signal is coming in and causing a shift in the charge on the opposite sides of the cell membrane, and I'm getting to a point where the charge differential is getting closer and closer to zero. I'm becoming more positive. All right, and this is what that depolarization means. How does that happen? Well, as that signal is coming in, it's causing those voltage gated channels, specifically the sodium ones, to start opening. And as they start opening down that axon, that's going to allow that positive sodium to start flowing into the cell. And now I'm causing the difference between negative and positive charges on the opposite side of that membrane to start becoming closer to equilibrium. Once I've gotten enough of that depolarization to occur where I've hit that threshold point, now I get that actual action potential to send. The signal from this point forward is like a bunch of dominoes, and I'm going to take it from hitting that first domino to allowing the last one to fall. There really is no stopping point once I've hit that threshold and the action potential gets sent. So when I look at the actual action potential itself, I've crossed that threshold and I'm now in that rising phase. That rising phase is getting that differential of voltage on either side of that cell membrane to become closer to zero and even extend past it. So we're getting more and more positive in terms of the voltage potential that I'm creating. How is this happening? Well, now I've crossed that threshold and now that membrane potential continues to increase. So if you look, right, here's my resting stage, here's my depolarization stage. Overarchingly in both of these, inside of the cell is more negative compared to the positive outside. Once I get to that rising phase, I've switched the charges. Enough of that positive that positive sodium has come in and flowed into the inside of the cell that now the internal cell overall has a positive charge compared to a now more negative charge on the outside. So I've flipped the charges from here to here. So once I hit that threshold, that rising phase now causes enough sodium to flow in to cause the change in that particular cell's charge. Once we've gotten that charge to completely reverse, right? So I'm now positive inside, negative outside. Then we're going to come into this falling phase of the action potential, where I'm now going to inactivate those voltage gated sodium channels and allow now the voltage gated potassium channels to open. So I've allowed for sodium to sort of hit its equilibrium point. That's what caused the change in those charges. Now I'm going to close them back off. And instead, now I'm going to open up the potassium ones instead and allow that potassium to start trying to diffuse down its concentration gradient. So the falling phase is now going to start reversing the process. So I've hit this sort of max potential in my positive voltage, and now I'm going to start coming back down. That's this falling phase, and we're accomplishing that by allowing that potassium to flow out. That potassium is going to continue to flow out, and we're actually going to undershoot that resting potential. So here's your resting potential right here. As we allow that falling phase to occur, we're actually going to kind of overfall, if that makes sense. We're going to undershoot the actual resting potential here. What does that mean? That membrane's permeability to potassium is actually slightly higher at rest than it is where your cells will start to actually close those potassium channels. Hopefully that makes sense. So we're going to bring that potassium and allow it to overshoot its equilibrium point above and beyond what we would want at that resting potential. So we allow a little excess potassium outside of the cell than we would actually want to restore that resting potential. That's where this undershoot comes in. But it's necessary in order to close off those potassium channels in order to reestablish a resting potential. So step 6 here is this refractory period, where I've got this little portion kind of right in here, all right, that's not actually labeled here on the diagram itself. That refractory period occurs after an action potential, and it's really where your cell's going to reestablish that resting potential. But during this period, there is no way for your cells to send a second action potential down the axon. It's a temporary inactivation of the entire neuron, really by inactivating your sodium channels. That's going to allow your cell to have the time to reset that resting potential. And once that resting potential is reestablished, then we can go ahead and send a new signal. So if I look at it from the axon as a whole, right, this is just a little snippet of that axon. Here is what we're looking at. So here you've got your overall internal cytosol of that axon. And what we do is, once again, think of it like the rolling of dominoes, right? So I'm going to send that action potential. I'm going to flip the charge by allowing the sodium to rush in, change the charge here, and then that's going to move on to the next portion of the axon. So here's the next set of sodium and potassium channels. While this one is now depolarizing, this one is repolarizing and pushing the sodium out. All right. Now we move it down again. So now this portion is allowing sodium to rush in. Back here, right, we're allowing the potassium to rush back out. And here we've now reset the membrane. So these action potentials travel in a single direction. They'll go, all of this buildup of reaching that threshold happens here at the axon hillox. So this is where it determines whether or not I've done enough depolarization to hit that threshold. Once I do, we then send these signals step by step all the way down the axon. So this signal can only ever travel in one direction towards those synaptic terminals down here at the other end of that axon, where we will more than likely probably release neurotransmitters or some other sort of signal to the next postsynaptic cell, whether that's another neuron that may send another action potential, or whether that's some sort of muscle or gland that I'm going to now activate. Those inactivated sodium channels during that refractory period prevent the action potential from being able to travel backwards. So that's where that refractory period really is important. It ensures that this signal only runs in one direction and can never backflow back up the axon, because that would be counterproductive. We're trying to get this information, say, from your brain down to your muscles so that you can move your hands to write your notes. We don't want that signal backflowing, because that's not the intended goal here. So when you look, if we kind of look at this, here's your resting potential. All right, you get your depolarization to that rising phase. That's where we've now hit this point. So that's where this connection comes in. That falling phase of the action potential is here. Okay, and then that resetting phase is here. So if I look down the same sort of column, if you will, of this picture and where it comes in to this particular voltage diagram, here's step 1 is the rising phase. Here in step 2, that's the falling phase. Here in step 3 is sort of that undershoot and reset. If I came here, all right, here's your resting potential, here's the rising phase, the falling phase, and then there would be a reset from there. So we're doing this constant peak and fall as we continue to move down the axon until we've gotten the message all the way down to those synaptic terminals.
What if everything you did, and thought, and felt could be communicated by pushing a button? It'd be like using the world's simplest app, one that just sends out a little ping, always at the same volume and length, to communicate everything from "it sure is cold in here" to "I love churros" to "boy, I sure would like to breathe sometime soon." Well, that is actually exactly how your neurons send all the impulses responsible for every one of your actions, thoughts, and emotions. When a neuron is stimulated enough, it fires an electrical impulse that zips down its axon to its neighboring neurons. But they've only got one signal that they can send, and it only transmits at one uniform strength and speed. What they can vary is the frequency or number of pulses, like this is distinct from this. And your brain can translate these signals, reading them like binary code, organizing them by location, sensation, magnitude, and importance, so that you know the difference between "turn up the thermostat" and "oh my gosh, I'm on fire." That buzz, that nerve impulse, is called the action potential. It's one of the most fundamental aspects of anatomy and physiology, and really life in general. It's happening inside of you right now, and we want to make sure that you understand what all that buzz is about. Before we delve into how neurons communicate, we gotta first understand a little bit of our old friend electricity. Basically, think of your body as a sack of batteries. No, I mean, you don't look like a sack of batteries. I'm just saying that your body as a whole is electrically neutral, with equal amounts of positive and negative charges floating around, but certain areas are more positively or negatively charged than others. And because opposite charges attract, we need barriers, or membranes, to keep positive and negative charges separate until we're ready to use the energy that their attraction creates. In other words, we keep them separated to build potential. A battery, just sitting on its own, has both a positive and a negative end, and the potential to release energy, but it doesn't do anything until it's hooked up to a flashlight or a phone or a kid's toy that lets those charges move toward each other, on the way converting electricity into light or sound or children's laughter. In much the same way, each neuron in your body is like its own little battery with its own separated charges. It just needs an event to trigger the action that brings those charges together. If you're thinking that this sounds more like engineering than anatomy, that might not be a bad thing. It might even help to think of your neurons in the same terms an electrician might use. Voltage, for example, is the measure of potential energy generated by separated charges. It's measured in volts, but in the case of your body, we use millivolts because it's a pretty small amount. In a cell, we refer to this difference in charge as the membrane potential. The bigger the difference between the positive and negative areas, the higher the voltage and the larger the potential. And just like there's voltage in your body, there's also current, the flow of electricity from one point to another. The amount of charge in a current is related both to its voltage and its resistance. Resistance is just whatever's getting in the the way of the current. Something with a high resistance is an insulator, like plastic, and something with a low resistance is a conductor, like metal. Now, when we talk about these concepts in terms of U, we're typically talking about how currents indicate the flow of positively or negatively charged ions across the resistance of your cell's membranes. And again, these membranes separate the charges, so they're what provide the potential to convert the electricity into something useful. Okay, now that we got electricity 101 down, let's see how it works inside your nervous system. A resting neuron is like a battery just sitting in that sack that is you. When it's just sitting there, it's more negative on the inside of the cell relative to the extracellular space around it. The difference is known as the neuron's resting membrane potential, and it sits at around negative 70 millivolts. Where do those charges come from? Outside of a resting neuron, there's a bunch of positive sodium ions floating around, just lingering outside the membrane. Inside, the neuron holds potassium ions that are positive as well, but they're mingled with bigger negatively charged proteins. And since there are more sodium ions outside than there are potassium ions inside, the cell's interior has an overall negative charge. When a neuron has a negative membrane potential like this, it is said to be polarized. Now, these ions didn't just show up in this arrangement on their own. This is all orchestrated by one of the most important bits of machinery in your nervous system, the sodium-potassium pump. This little protein straddles the membrane of the neuron, and there are tons of them all along the axon. For every 2 potassium ions it pumps into the cell, it pumps out 3 sodium ions. This creates a difference in the concentration of sodium and potassium, and a difference in charges, making it more positive outside the neuron. This difference is an electrochemical gradient, and you probably know enough about biology by now to know that nature hates gradients. It wants to even out all of those inequalities in concentration and in charge to restore balance. But the only way to even out that gradient is for the ions to pass across the membrane. Thankfully, the sodium-potassium pump isn't the only way in or out of the cell. The membrane is also riddled with ion channels, large proteins that can provide safe passage across the membrane when their respective gates are open. And these gates open and close for different reasons depending on their structure and purpose. Most are voltage-gated channels, which open at certain membrane potentials and close at others. For example, sodium channels in your neurons like to open around negative 55 millivolts. But some others are ligand-gated channels. They only open up when a specific neurotransmitter, like serotonin or a hormone, latches onto it. Then we also have mechanically gated channels, which open in response to physically stretching the membrane. In any case, when the gates do open, ions quickly diffuse across that membrane down their electrochemical gradient, evening out the concentrations and running away from other positively charged ions. This movement of ions is the key to all electrical events in neurons, and thus is the force behind every single thing we think, do, and feel. Of course, not all of your body's electrical responses are the same, and neither are the flows of ions going in and out of your neurons. If only a few channels open and only a bit of sodium enters the cell, that causes just a little change in the membrane potential in a localized part of the cell. This is called a graded potential. But in order to send long-distance signals all the way along an axon, you need a bigger change, one big enough to trigger those voltage-gated channels. That is an action potential. And your best bet for making that happen is to depolarize that resting neuron. I mean, cause a big enough change in its membrane potential that it'll trigger the voltage-gated channels to open. It all starts with your neuron sitting there at resting state. All of the ion channels are closed and the inner voltage is resting at negative 70 millivolts. And then something happens. Some environmental stimulus occurs, say like a spider brushes up against a tiny hair on your knee, triggering those sodium channels to open, increasing the charge inside the membrane. Now, the stimulus and the resulting change have to be strong enough to cross a threshold for the true action potential to kick in, and that threshold is about negative 55 millivolts. Remember that number, because this is an all-or-nothing phenomenon. If the stimulus is too weak and the change doesn't hit that level, it's like a false alarm. The neuron just returns to its resting state. But kind of like Doc Brown hitting 1.21 gigawatts in the DeLorean, once it hits that threshold, you're not going to travel in time, but you are going to see some serious action potential. At that threshold, the voltage-gated sodium channels open, and there are tons of these, so all of the positive sodium ions rush in, making the cell massively depolarized. So much so that it actually goes positive, up to about positive 40 millivolts. This is action potential in action. It's really just a temporary reversal of a membrane potential, a brief depolarization caused by changes in currents. And unlike graded potentials, which are small and localized, an action potential kicks off a biological chain reaction which sends that electrical signal down the axon. Because each of your neurons has lots of voltage-gated sodium channels, so when a few in one area open, that local current is strong enough to change the voltage around them, and that triggers their neighbors, which triggers the voltage around them, and so on down the line. As soon as all that's underway, the process of repolarization kicks in. This time the voltage-gated potassium ion channels open up, letting those potassium ions flow out in an attempt to rebalance the charges. If anything, it goes too far at first, and the membrane briefly goes through hyperpolarization. Its voltage drops to -75 or so millivolts before all of the gates close and the sodium-potassium pumps take over and bring things back to their resting level. Now, when part of an axon is in the middle of all this and its ion channels are open, it can't respond to any other stimulus, no matter how strong. This is called the refractory period, and it's there to help prevent signals from traveling in both directions down the axon at once. So that is the surprisingly simple app that your nervous system uses to let you experience the world. And because the voltages in this process are always pretty much the same, the initial threshold around -55 millivolts and the peak depolarization at 40 millivolts, your neurons only communicate in a single monotone buzz. It doesn't matter if it's a spider on your knee or an elephant, a paper cut or a stab wound, the strength of that action potential is always the same. What does change is the frequency of the buzz. A weak stimulus tends to trigger less frequent action potentials, and that includes if the stimulus is coming from you, like your brain telling your muscles to perform some task. If I need to do something delicate, like pick up an egg, the signal is low frequency. But a more intense signal, like trying to crush a can, increases the frequency of those action potentials to tell your muscles to contract harder, and the message turns into something that you can't ignore. Action potentials also vary by speed or conduction velocity. They're fastest in pathways that govern things like reflexes, for example, but they're slower in places like your glands, guts, and blood vessels. And the factor that affects a neuron's transmission speed the most is whether there's a myelin sheath on its axon. Axons coated in insulating myelin conduct impulses faster than non-myelinated ones, partly because instead of just triggering one channel at a time in a chain reaction, a current can effectively leap from one gap in the myelin to the next. These little gaps are the delightfully named nodes of Ranvier, and this kind of propagation is known as saltatory conduction, from the Latin word for leaping. But what happens when an action potential hits the end of its axon and is ready to do more than leap and jump all the way to another neuron? That you will find out next time. Today, you learned how your body is kind of like a big bag of batteries, and how ion channels in your neurons regulate this electrochemistry to create an action potential from resting state to depolarization to repolarization and a brief bout of hyperpolarization. Thanks for watching, especially to all of our Subbable subscribers who make Crash Course possible for themselves and for everyone else. To find out how you can become a supporter, just go to Subbable.com. This episode was written by Kathleen Yale, the script was edited by Blake Tepestino, and our consultant is Dr. Brandon Jackson. It was directed by Nicholas Jenkins and Michael Aranda, and our graphics team is Thought Cafe. One more thing before you leave. We like Crash Course a lot, and we hope that you like Crash Course a lot, but I kind of feel like Crash Course is only useful for a certain segment of the population. Like, once you get to a certain age, then it's good, and then forever, it can be helpful to people. But younger people, not so much. And so, we are creating Crash Course Kids, hosted by Sabrina Cruz from Nerdy and Quirky. Crash Course Kids will start out focusing on 5th grade science, but we'll keep expanding to other topics as the channel grows. Sabrina will be talking about food chains and gravity and how the sun works and how plants eat and why flamingos are pink and many other topics. Oh, and another note, teachers, you can rest assured that we've got you covered. There will be info about the standards we've used to make sure that we're doing our very best to help you out. So if you are a teacher, or you know a teacher, or you know a child, or you know someone who has a child, or you've ever seen a child, you can tell them to go to youtube.com/crashcoursekids and subscribe, and you can go do that as well if you would find that kind of content useful or interesting.